Welcome to today's episode on industrial instrumentation. Today we'll talk about the different statistical parameters that are required for understanding of the industrial instrumentation subject. In due course, we'll cover the following topics: dispersion, also called variability, scatter or spread; coefficient of dispersion, COD; variance; standard deviation denoted by sigma; root mean squared error, RMSE; absolute error, AE; mean absolute error, MAE; percentage error of estimate, PE. Then we'll come across mean square error, MSE; mean absolute percentage error, MAPE; mean absolute deviation, MAD or mean ratio; residuals; sum of squares of error, SSE; factor analysis; Eigen Value and Eigen Vector. Dispersion is also known as variability, scatter or spread. It is the extent to which a distribution is stretched or squeezed. Common examples of statistical dispersion are the variance, standard deviation, and interquartile range. Coefficient of dispersion COD is a measure of spread that describes the amount of variability relative to the mean, and it is unitless. Numerically, it is given as COD equal to sigma by mu whole into 100. Variance is the expectation of the squared deviation of a random variable from its mean, and it informally measures how far a set of random numbers are spread out from the mean. It is calculated by taking the differences between each number in the set and the mean, squaring the differences to make them positive, and then dividing the sum of the squares by the number of values in the set. The variance provides the user with a numerical measure of the scatter of the data. Numerically, variance is given as sigma square equal to summation x minus mu whole square whole by n, or summation x square by n minus mu square, where mu denotes mean, that is summation x by n. Standard deviation sigma is a measure used to quantify the amount of variation or dispersion of a set of data values. It is a number that tells how measurement for a group are spread out from the average mean or the expected value. A low standard deviation means most of the numbers are very close to the average, while a large value indicates that the data to be largely spread out. The standard deviation provides the user with a numerical measure of the scatter of the data. Numerically, sigma equal to square root of 1 by n summation x minus mu whole square, where mu is the mean. The next important statistical parameter is root mean squared error, also called RMSE. It is used to measure the differences between values, sample and population values, predicted by a model or an estimator, and the values actually observed. RMSE is numerically represented as root of summation x observed minus x model whole square by n. The absolute error is the magnitude of the difference between the exact value and the approximation. The relative error in the absolute value divided by the magnitude of the exact value. AE is numerically represented as x measured minus x actual. Mean absolute error, MAE, is a quantity to measure how close forecasts or predictions are to the eventual outcomes. It is an average of the absolute errors. The simplest measure of forecast accuracy is MAE. The relative size of error is not always obvious. MAE is given as 1 by n summation I 1 to n mod of AE, where AE denotes absolute error. Percentage error of estimate, PE, is the difference between the approximate and the exact value as a percentage of the exact value. Percentage error is given as mod of exact value minus approximate value by exact value whole into 100. Mean square error is also known as mean square deviation, or MSD. It measures the average of the squares of the errors or deviations, that is, the difference between estimator and that is estimated. MSE is given as 1 by n summation I equal to 1 to n mu minus xi whole square, where mu is the mean. Sum of squares of error SSE is also termed as residual sum of squares RSS and sum of squared residuals SSR or sum of squared errors SSE. It is the sum of the squares of residuals, deviations predicted from actual empirical values of data. It is a measure of the discrepancy between the data and an estimation model. A small SSE or RSS indicates a tight fit of the model to the data. It is used as an optimal criterion in parameter selection and model selection. Sum of squares of error SSE is given as summation I 1 to n xi minus mu whole square. Mean absolute percentage error is also termed as mean absolute percentage deviation MAPD. It is a measure of predicting accuracy of a forecasting method in statistics. MAPE is numerically shown as 100 by n summation I equal to 1 to n mod of actual value minus forecasted value by mod of actual value. Mean absolute deviation is the relationship between two numbers indicating how many times the first number contains the second. It is an alternative to MAPE, better suited to intermittent and low volume data. It is a robust measure of the variability of a univariate sample of quantitative data. The MAD of a set of data is the average distance between each data value and the mean. Numerically, MAD equal to 1 by n summation I equal to 1 to n mod of xi minus mu. Residuals is the difference between the observed value of the dependent variable y and the predicted value y dash. Each data point has one residual. Both the sum and the mean of the residuals are equal to 0. R is given as R equal to observed y value minus predicted y value. Factor analysis is a useful tool for investigating variable relationships for complex concepts, allowing researchers to investigate concepts that are not easily measured directly by collapsing a large number of variables into a few interpretable underlying factors. Eigen vector is a vector which, when operated on by a given operator, gives a scalar multiple of itself. The eigen vectors E1, E2, so on and so forth till EP for a matrix A are obtained by solving the expression A minus lambda j I whole into Ej equal to 0. Here we have the difference between the matrix A minus the jth eigenvalue times the identity matrix I. This quantity is then multiplied by the jth eigenvector and set it all equal to 0. This will obtain the eigenvector Ej associated with the eigenvalue lambda j. If we define a P cross P matrix A, we are going to have P eigenvalues lambda 1, lambda 2 till lambda P. These values are obtained by solving the equation mod of A minus lambda I equal to 0. On the left hand side we have a matrix A minus lambda times the identity matrix. When we calculate the determinant of the resulting matrix, we end up with a polynomial of order P. Setting the polynomial equal to 0 and solving for lambda, we obtain the desired eigenvalues. We will have P solutions in general which are not necessarily unique. We will have P solutions in general which are not necessarily unique, as already mentioned. Eigenvalues are a special set of scalars associated with a linear system of equations that are sometimes known as the characteristic root, characteristic value, and proper value or latent roots. The determination of eigenvalue and eigenvector is extremely important where it is equivalent to matrix diagonalization and arises in such applications as stability analysis and others. Eigenvalue and eigenvectors are used for computing prediction and confidence ellipses, principal components analysis and factor analysis. Here we'll try to go through an example to figure out how eigenvalues are determined. Let's consider a 2 cross 2 matrix named R. R is such given as R equal to 1 row, row 1. Therefore, mod R minus lambda I is equal to mod 1 row, row 1 minus 1001. Calculating the determinant with the matrix with 1 minus lambda on the diagonal and row on the off diagonal, we have 1 minus lambda row 1 minus lambda equal to 1 minus lambda whole square minus row square equal to 1 minus lambda whole square minus 2 plus 1 minus row square. Setting this expression equal to 0, we have lambda square minus 2 lambda plus 1 minus row square equal to 0. We have the formula a square plus by plus c equal to 0, which boils down to y equal to minus b plus minus root over b square minus 4ac by 2a. Thus, solving for lambda, we get lambda equal to 2 plus minus under root 2 square minus 4 into 1 minus row square by 2 equal to 1 plus minus under root 1 minus 1 by row square equal to 1 plus minus row. Therefore, eigenvalues are lambda 1 equal to 1 plus row and lambda 2 equal to 1 minus row. To obtain the corresponding eigenvectors, we must solve the expression r minus lambda I whole into e equal to 0, or 1 row 1 minus lambda into 1001 whole into e1 e2 equal to 0 0, which boils down to 1 minus lambda row 1 minus lambda into e1 e2 equal to 0 0. This will yield 1 minus lambda into e1 plus row e2 equal to 0, row e1 plus 1 minus lambda e2 equal to 0. This does not have a unique solution. The additional condition is that the sum of the squared values of e1 and e2 is equal to 1, that is e1 square plus e2 square equal to 1. If we consider the first equation, 1 minus lambda into e1 plus row e2 equal to 0, we get e2 equal to minus 1 minus lambda by row into e1. Therefore, e1 square plus 1 minus lambda whole square by row square e1 square equal to 1. Again, lambda equal to 1 plus minus row from the previous solution. Therefore, we get 2 e1 square equal to 1, that tends to e1 equal to 1 by under root 2, e2 equal to 1 by lambda by row e1 whole in negative equal to 1 by under root 2. Therefore, the final solution we get 1 by under root 2, 1 by under root 2 for lambda 1 equal to 1 plus row, and 1 by under root 2 minus 1 by under root 2 for lambda 2 equal to 1 minus row.